Hi friends, let's now have a brief revision class in kinematics. Instantaneous velocity is ds by dt. Whenever we say velocity, unless otherwise specified, we mean instantaneous velocity. Similarly, whenever we say acceleration, we mean instantaneous acceleration unless otherwise specified. Fine. Okay, so average velocity is total displacement by total time. Instantaneous acceleration is time derivative of velocity or dv by dt. Okay, and average acceleration is total change in velocity by total time. Okay, total change in velocity by total time. Okay, this could be something like v minus u by time duration in which this change in velocity has taken place. U is initial velocity, v is velocity at the end of time t. Fine. Equations of motion for a body moving in a straight line with uniform acceleration. We know by definition acceleration is change in velocity by time. So this will give you, okay, v minus u is at or v equal to u plus at. Fine. Now, okay, for a body moving with uniform acceleration, average velocity can be written as u plus v by 2. Okay, in general, average velocity is total displacement by total time. That is valid under all conditions, whether the acceleration is constant or variable or zero. But when acceleration is constant, average velocity can be written as u plus v by 2. Okay, of course, sometimes when acceleration is variable also, this formula is applicable, but that's beyond our scope at this stage. Fine. Somehow, this formula, u plus v by 2, is definitely valid whenever acceleration is constant. Okay, whether the path is straight line or parabola, doesn't matter. Whenever acceleration is constant, this formula is valid. Fine. Okay, now, somehow we are considering motion of a body in a straight line with uniform acceleration. Alright. And this average velocity can be written as total displacement by total time. So this, okay, we need displacement suppose. So safely you can write down S equal to average velocity into time. Alright. And now we have obtained V equal to U plus AT. Plug in here. For V you write U plus AT. We'll end up getting S equal to UT plus half AT square. Okay. In the same equation, instead of substituting for V, if we write, substitute for U, U is V minus AT, right? V minus AT for U, you'll end up getting VT minus half AT square. Okay, if final velocity is known, you can go by the formula VT minus half AT square. If initial velocity is known, you can go by UT plus half AT square. Okay, and same displacement can also be written directly like this, average velocity into time. So U plus V by 2 into T, fine. Okay, and displacement of the body in nth second, okay, is u plus a n minus half. Okay, mind you, this is displacement in n seconds minus displacement in n minus 1 seconds. Okay, so here suppose this nth second is say 10th second or 8th second or 9th second, doesn't matter. U is the velocity at t equal to 0. Alright, so like for example, t equal to 0, t equal to 1, this is the first second ends at 1, second ends at 2, third second ends at 3, or third second begins at 2, fine. So even if we are computing the displacement in the third second, u is the velocity at t equal to 0 and not at the beginning of third second. Is it clear? Velocity and displacement are related by the equation v squared minus c squared equal to 2as. Okay, in fact it is 2a dot s basically, but somehow you can write down for a body moving in a straight line 2as. Fine. As we already said, acceleration is rate of change of velocity. Direction of acceleration will be same as the direction of change in velocity vector. In fact, direction of average acceleration will be same as the direction of total change in velocity. Okay, just like that, velocity's direction is same as that of displacement vector. Okay, average velocity's direction will be same as the direction of total displacement. Fine. Let us consider the general cases like acceleration, dv by dt. Okay, this implies dv is a dt. Fine. Taking integration on both sides. So integral dv is integral a dt. Okay, so suppose initial velocity is u and velocity at time t is v. Initial means at time t equal to 0. This is the general equation. Fine. Okay, so this is going to become v minus u and this is integral a dt. Area under 80 grams. Fine. Equation 1. Now, okay, coming to acceleration. Coming to velocity. Velocity is ds by dt. Okay, this implies ds equal to v dt. Alright. So, now integrating on both sides. At t equal to 0, let the position is s0. At time t, let the position is, s. So this is going to be s minus s0. Alright. Or displacement. Change in position vector is called displacement. This is equal to integral v dt. 0 to t. Alright. Let this be equation 2. Now acceleration can also be written as dv by dt multiply by ds and divide by ds. This ds by dt can be replaced by v. So this becomes v dv by ds. Fine. Cross up. Okay, we get v dv is equal to a ds. Fine. Now integrate on both sides under appropriate limits. Okay. So here say u to v and this is ADS. Alright. Say from S0 to S. Okay. This becomes v square by 2 under this limits. It becomes v square minus u square by 2 and that is equal to integral ADS under the limits S0 to S. Fine. So, okay. These are the equations which we need to remember. Mind you, these are the general cases. Are applicable whether the acceleration is constant or variable. In case the acceleration is constant, automatically this formula will turn out to be v minus u equal to at, because this a can be taken out and then it will be t. So v minus u becomes at here, and here it becomes displacement. This basically is displacement. Change in position vector is called displacement. This becomes, ut plus half it squared. Okay, and this becomes v square minus u square equal to as. In case acceleration is constant. Fine. Even though we write acceleration as v minus u by t, direction of acceleration has nothing to do with direction of either initial velocity or final velocity. Alright. Direction of acceleration is basically in the direction of force according to the equation F equal to ma. Fine. For example, if a body is projected, irrespective of the direction of throw, this side, drop, give whatever velocity, acceleration is always down, irrespective of the direction of either initial velocity or final velocity, because gravitational force is down and therefore acceleration is down. Fine. Suppose a particle is starting from rest with a constant acceleration, then ratio of displacements in successive equal intervals of time will be 1:3:5:7 and so on. Okay, in odd number means 2n minus 1. Okay, here it need not be 1 second intervals. U is 0 and A is constant is must. Ratio of displacement successive equal interval of time. It would be first half second, next half second, next half second, or first 10 second, next 10 second, next 10 second and so on. Fine. Okay, so we can easily get that at least for 1 second. We know S1, U is 0, fine. A into n minus half, n is 1, first second I'm telling, and this is going to be A by 2. In fact, this should also help you to remember something, like whenever a particle is starting from rest with uniform acceleration, displacement in first second is numerically equal to A by 2. Alright, for example, for a drop body, U is 0, displacement in the first second of fall will be G by 2. Okay, while coming down. Of course, when you project it up, displacement in the last second while going up equal to first second while coming down equal to G by 2 irrespective of the initial velocity. Fine. Okay. Now, so this is in the first second. Coming to the second, this is going to be 0 plus A, 2 minus half is going to be 3 by 2. Alright, this is A by 2, 3A by 2, then 5A by 2, so ratio is going to be 1:3:5 and so on. Fine. Now, whenever a body is starting from rest and moving with uniform acceleration, displacement at time t, u is 0, half a t square. A is constant, so I can safely write down kt square. It is proportional to t square. Fine. And now I can easily say displacement at the end of 1 second, at the end of 2 seconds, at the end of 3 seconds and so on from the beginning. That ratio is going to be 1 square is 2, 2 square is 2, 3 square is 2 and so on. Is that clear? N square and so on. Fine. Okay, now again u is 0, a is constant. Okay, particle starting from rest moving with uniform acceleration. Ratio of times taken to cover successive equal displacements. Equal displacements now. Ratio of time taken to cover will be root 1 minus root 0 is 2, root 2 minus root 1 is 2, root 3 minus root 2 is 2. Okay, nth interval it will be root n minus root n minus 1 and so on. Fine. Basically this is 1 and this is root 2 minus 1. And rest you can follow. Fine. So I have written like this so that you can remember first term starts with root 1, second term starts with root 2, nth term starts with root n. Fine. Okay, so let's just derive the ratio of times taken to cover successive global displacement formula. U is 0, acceleration is constant given. So time taken to cover first S using the equation S equal to half a t square because U is 0. Alright. So we end up getting time taken to cover first S as 2S by A. Alright. So let me write it here 2S by A. Now, time taken to cover second S will be time taken to cover 2S minus time taken to cover S. Fine. This. Okay, fine. So it's going to be time taken to cover 2s displacement from beginning will be root 2 times 2s by a, because for displacement we'll be writing 2s now, minus time taken to cover first s is obviously this is 2s by a within root. Now time taken to cover third s will be time taken to cover 3s from beginning, and that's going to be root 2, instead of s we'll be writing 3s by a, and minus time taken to cover first 2s, that will give you time taken to cover third s. So time taken to cover 2s we need to write here. So something like this and so on. Now this 2s by a you can easily take out common and cancel, fine, because ratio doesn't change. So what's left out here is, okay, root 2s by a is gone, 1, here root 2 minus 1, and here root 3 minus root 2, and so on. You will end up getting like root 4 minus root 3, and in the nth interval it will be root n minus 1, fine. So this 1 I'm writing as root 1 minus root 0, and for this one I'm writing root 1. So it will end up like, first term starting with root 1, second term starts with root 2, third with root 3, nth term with root n, and so on, fine. So here this is a ratio of times taken to cover successive equal displacements for a body starting from rest with uniform acceleration, fine. As we already said, average velocity for a body moving with uniform acceleration is u plus v by 2. Okay, that is also equal to the instantaneous velocity at half the time. Fine. In the equation v equal to u plus at, alright, just write a as v minus u by t and time as t by 2. You will end up getting velocity as this. So average velocity for a body moving with uniform acceleration is equal to instantaneous velocity at half the time, not at half the displacement. When it comes to half the displacement, that's going to be the midpoint of the path, say s by 2 and s by 2. At that point, what will be the velocity? If initial velocity is u and your velocity at time t is v, okay, velocity at midpoint of the path is going to be root u square plus v square by 2, everything under root. This is going to be velocity at midpoint of the path or at half the displacement. It's quite simple to get this. Okay, here apply the equation v square minus u square equal to 2as by 2. And for this part of the equation apply, this is final velocity now, v square minus v dash squared equal to 2as by 2. Alright, let a be the acceleration over here. Fine. Now when right hand terms are equal, left hand terms are also equal. So let us equate the left hand terms here now. V dash squared minus u squared equal to v squared minus v dash squared. Simplify it, you will end up getting this term, velocity at midpoint of the path. Okay, this formula should be used very frequently whenever you need velocity at midpoint of the path. For example, a body is given that it's projected upward with a velocity u. What is the velocity at half the max height? Okay, half the max height means velocity, here velocity is 0, we know. Half the max height is midpoint of the path. Use the same equation. But this is 0, so this will be what? Obviously u by root 2. Fine. Something like this. Suppose it's given a bullet fired 500 into a plank, comes out with 100 meters per second. Thickness of the plank is given 80. Instead of 80, suppose the thickness of the plank is just 40 centimeters. With what velocity the bullet will come out? Again the same thing. 40 is going to be midpoint of this 80 centimeter. So you should use the formula for midpoint. Fine. Root over this square plus this square by 2. Fine. So 100 common term out. Alright. Now 5 squared plus 1 squared is going to be 26 by 2. So it's going to be 100 root 13. This is the velocity with which the bullet will come out from a plank which is just 40 centimeter thick. Fine. Suppose it's given a train. Okay, engine of the train crosses an electric pole with a velocity u. Okay, tail end of the train crosses this electric pole with a velocity v. With what velocity midpoint of the train crosses the pole? Rest and motion are relative. You can imagine train is at rest. Pole is going with uniform acceleration, crosses the engine with u and crosses the tail with v. So this pole will cross midpoint with same formula, root over u square plus v square by 2. Fine. And suppose a body is moving with a constant velocity v1 for time t1 with a velocity v2 for time t2. What's going to be the average velocity? By definition, average velocity is total displacement by total time. Fine. So here displacement is v1 t1 because there's no half a t square. So displacement s1 is v1 t1 and displacement s2 is v2 t2. Total displacement by total time is t1 plus t2. Okay, you can extend it up to whatever length is v3 for time 3, t3 with velocity v4 for time t4 and so on. So this is going to be something like this, total displacement by total time, right? Similarly, if a body is having an acceleration a1 for time t1, an acceleration a2 for time t2, an acceleration a3 for time t3 and so on, then average acceleration as usual, total change in velocity by total time. We know acceleration a1 will be change in velocity 1 in that duration by time t1 suppose. So change in velocity 1, this delta v1 will be a1 t1. So average acceleration is total change in velocity by total time. Alright. Well, total time is t1 plus t2 and so on. Okay. So what is delta v1? That is a1 t1. So safely I can write down here a1 t1 plus a2 t2 and so on by total time t1 plus t2 and so on. Mind you, numerator is vector here, change velocity. You need to add as if they are vectors, using lots of vectors. Okay, even if they are in different direction, you can add them. Okay, say if delta v1 and delta v2 are in mutually perpendicular direction, this numerical value of this value, magnitude is going to be under root delta v1 squared plus delta v2 squared, right? Something like this. Is that clear? This particular thing. And if n1 part of the displacement is covered with velocity v1, n2 part of the displacement is covered with velocity v2, what is the average velocity? Okay, by definition, average velocity, total displacement by total time. Total displacement is n1 part of s plus n2 part of this. Just take out s common. You will have something like this. Alright, this is total displacement. Now by total time I need to, total time, it is displacement by v1. n1s by v1 is t1. Alright, and n2s by v2 is t2. Fine. Okay, like we know distance n1s equal to v1 t1. Fine. So t1 will be n1s by v1. This is t2. Total displacement by total time. We can easily take out s common from here. Okay, s you can take it out, and then you can easily cancel this. Fine. And here you take LCM in the denominators. Denominator you will have v1 v2, and here n1 v2 plus n2 v1. So that will go in the numerator, and you will end up getting something like this: n1 plus n2 into v1 v2 by n1 v2 plus n2 v1. Fine. In this, as a specific case, if n1 part of the distance is covered with velocity u and n2 part with v, in fact, let us call it half the distance with u and other half with v, in fact, then average velocity is going to be half plus half 1 uv. 1 uv means uv by half u plus half v. That 2 will come in the numerator, and average velocity is going to be 2 uv by u plus v for a body moving with, velocity u for half the displacement, and with velocity v, the other half displacement. Average velocity is going to be 2 uv by u plus v. Fine. Okay. And in case it's traveling, say, n1 part of the displacement with velocity v1, n2 part of the displacement with velocity v2, n3 part of the displacement with velocity v3, then you can just stretch it and you will end up getting the same way as n1 plus n2 plus n3 into v1, v2, v3, and here you will have n1, it will be like, n1s by v1 plus n2s by v2 plus n3s by v3. So LCM will be v1, v2, v3, and here it will be n1, v2, v3. So n1, v2, v3. Okay, n2 then 1, 3. Then n3 means 1, 2. Is that clear? And in this case, if something like this, first 1/3 displacement with velocity u, second 1/3 with velocity v, and the last 1/3 with velocity w. Suppose in that case, this is 1/3 plus 1/3 plus 1/3 uvw by 1/3 uv plus 1/3 vw plus 1/3 uw. 3 will come up. Okay, you will end up getting 3 uvw by uv plus vw plus uw. Something like that. That's going to be the average velocity when a body covers 1/3, 1/3, 1/3 displacements with u, v, w respectively. Fine. For a body moving with uniform acceleration, difference in displacement in successive second gives acceleration. If Sn is displacement in the nth second and Sm in the mth second, even this is going to be acceleration. This is valid for a body moving with uniform acceleration, whether the path is straight line or parabola. Fine. Let's now proceed to vertical motion by gravity. We know when a body is moving freely near the surface of the earth, it will experience acceleration due to gravity, which is about 9.8 meter per second square vertically downward. Its value can be taken as constant for small heights compared to radius of the earth. Even 100 kilometers is small compared to radius of the earth, which is about 6,400 kilometers. Fine. Now, suppose the body is projected vertically up with initial velocity u. This is about 6g meter per second. Fine. So velocity at time t is required means we will be using the formula v equal to u plus at. I'm taking upward direction positive. So all the vectors up will be positive and g is down. So I'm taking negative. Fine. So these two quantities, this is given, this is known. So this will give you a relationship between velocity and time. So suppose we need velocity 2.5 seconds after projection. Just right here 2.540, you will get velocity 2.5 seconds after projection. While going up, every second body will lose a velocity equal to g. If g is 9.8, every second velocity will decrease by 9.8 meter per second. Fine. And if moving down, every second velocity will increase by 9.8 meter per second. Something like that. So if velocity and height of this body are related by the equation v square minus u square equal to minus 2gh. Fine. Here u is given, g is known. So this is the relationship between velocity and height. Clear? velocity at the topmost point will be 0. You can use this equation. You see, so for example here, velocity is u is 6g, in fact 58.8 minus g 9.8, t 1, 2, 3, as time is increasing, when time is 6, exactly 6.0, at that instant this is going to become 0, fine. So, a moment before that, if you take 5.9 as time, velocity is still positive and the body is still going up. And if this time is 6.1, say slightly more than 6.001 also, velocity becomes negative, means body has already started coming down. So exactly at t equal to 6, the body will be at the topmost point. So instantaneous velocity will be 0 at t equal to 6. A moment later, body has already started coming down. A moment before, it's still to go up. That means at the topmost point, velocity of the body is going to be 0. Fine. And its velocity will remain 0 for 0 seconds. It's not going to stay there, have a cup of coffee and come back. Okay, only instantaneous velocity is going to be 0. A moment before, it still has to go up. A moment later, it has already started coming down. Okay, velocity becomes 0 only at that particular instant. Mind you, acceleration is not 0 at the top. Only velocity has become 0. When you see velocity 0, don't say acceleration 0. When you see position vector 0, don't say velocity 0. Whatever you see, just tell that. Fine. So, here, only velocity becomes 0 at the top. Acceleration is still there because force is still there. Earth is still attracting it. F is there. F is there means ma is there. Acceleration is there, right? For this body, what is time of ascent? Time of ascent is time taken for upward journey, means time taken until its velocity becomes 0. So just substitute here 0, you'll end up getting minus u equal to minus gt, or time of ascent is going to be u by g. Fine. Alright. Time of descent we need to compute. Before computing time of descent, let us find out time of flight. Time of flight is to go up and come back. Fine. Time taken to go up and come back. So let's use this equation, h equal to ut minus half gt square, relationship between height and time for this particular body. Okay, here u is given and g is known. So this is straight away relationship between height and time. Like if t is 2 seconds, what is the height? If t is 4 seconds, what is the height? Just substitute it, you will get the height. Fine. Okay, so now, suppose we need time of flight, means time to go up and come back. So displacement should become 0. Just substitute here 0. You'll end up getting something like ut minus half gt squared. Okay, on solving you will end up getting either t equal to 0 or t equal to 2u by g. Okay. That means at t equal to 0 particle is here, at t equal to 2u by g particle is here. The difference in time is the time in which the body is going up and coming back. So this becomes time of flight. We just now computed time of ascent as u by g. There's the time to go up. Okay, if you call u by g as 1 banana, 2u by g will be 2 bananas. Fine. Time to go ahead and come back. 2 bananas minus 1 banana will be 1 banana. So time, okay, 2 bananas minus 1 banana will be time to come back. So time of ascent equal to time of descent equal to u by g, neglecting air friction, and time of flight is 2u by g for a vertically projected body. Fine. We know its velocity and height are related by this equation. Now, suppose we need max height. Max height is nothing but height when velocity becomes 0. So when this velocity becomes 0, at that time whatever value of height we obtain, that's going to be the maximum height reached by this body. So minus sign we can now safely cancel out, and we'll end up getting u squared by 2g as h max, or maximum height for a body projected up with velocity u. Is it clear? Let's now proceed to case 2 in vertical motion. Suppose a body is dropped from a top of a tower of height h, initial velocity 0, acceleration is g downward. Let's take downward direction positive. Okay, so and displacement by the time it reaches the ground is going to be h is downward, so I'm taking positive. Suppose we need velocity with which it hits the ground. Okay, u v as means we need to use the equation v square minus u square equal to as, when we end up getting v as 2gh, fine, s is h here. So it will hit the ground with this velocity. Okay, instead of velocity, if time is required, at what time it hits the ground? Use the equation s equal to ut plus half it square. We end up getting the time of fall as root 2h by g. Okay. So, when a body is dropped from height h, it will hit the ground with a velocity root 2gh. That means if we project a body with root 2gh upward, it will reach max height h. Okay. And when a body is dropped from height h, it will hit the ground in this much time, time of fall. And if a body is projected upwards, and if it is given that it reaches a max height h, definitely time of ascent will be this much. Because we know at the topmost point its velocity is going to become 0. And second half of the journey, that means while returning, it is starting from rest. So it's like a dropped body. And we know for a dropped body, whatever height it has traveled, it has to fall back through the same height. For a dropped body, we have already seen time of fall is this. And we also know for a vertically projected body, time of ascent and time of descent are equal. So time of descent, time of fall is this, means time of ascent also will be same, root 2h by g. So when a body is projected from ground and max height is given as h, then time of ascent is going to be root 2h by g. We know initial velocity is 0 and acceleration is g. If velocity at time t is asked, obviously v equal to u plus at u is 0, it becomes gt. That means at the end of 1 second will be g, at the end of 2 seconds 2g, at the end of 10 seconds 10 g meter per second. Fine. So every second velocity will increase by g for a drop body or for a body which is moving downwards. Fine. Let us now consider a case where a body is projected with initial velocity u vertically upward from the top of a tower of height h. Okay, let us take upward direction positive. Okay, initial velocity u, acceleration is downward, so minus g. Okay, initially body is here, finally it's here when it hits the ground. So displacement is this much. Okay, displacement, when we are taking displacement, we should not bother about the path followed by the body, just initial and final. Fine. And displacement is downward, initial position, final position. So until it hits the ground, or when it hits the ground, displacement is minus h. Fine. And if time is asked, time taken for this particular body to hit the ground, we need to use the equation s equal to ut plus half at square. That means minus h equal to ut minus half gt square. There's a quadratic in t. Solve it, you will get two values. Okay, somehow one will be negative, which we disregard in this case. So on solving this, we'll end up getting like this: u by g plus root u square plus 2gh by g. Okay. Okay, this can be written as u by g is time to go up, in fact, time of ascent, and the other term, this term can be written as v by g. Alright, this is time of ascent and this is time of descent. Alright, if height of the tower becomes 0, then in u by g, so automatically when this is 0, even this will turn out to be u by g, and time of flight will become 2u by g, right? Okay, so remember, for this particular term, I am writing v. So that means, instead of time, if velocity with which it hits the ground is asked, we need to use the equation v square minus u square 2as, and we will end up getting this particular value for velocity. Okay, so velocity with which it hits the ground, root u squared plus 2gh. And this particular equation for velocity is valid whether you project this body upward or horizontally or in any direction, as long as you throw a body with speed u from height h. In all cases, it will hit the ground with the same final speed. You can use conservation of energy to get this, fine. But the time formula, this particular time of, time taken to hit the ground, to go up and come back, that is valid only for a vertically projected body, but speed is valid for, this particular value for speed is valid for bodies projected in any direction with equal speed u, right? Somehow, for a body projected vertically upward, this is the time u by g to go up and v by g to come back, and this is the speed v with which it will hit the ground, fine? Now consider a balloon which is going up with a constant velocity u, and if h is the height of the balloon when the stone is dropped from it. Due to inertia of motion, initially this particular stone will have same initial velocity as that of the balloon. Of course, now it will have acceleration due to gravity g downwards, because it's moving freely under gravity. Okay, so it will go up and come back. Now, if you just compare the motion of this stone which is dropped from a balloon which is going up with velocity u, and this stone which is projected vertically upward from the top of a tower of height h. Initial velocity u, acceleration g down, okay? I mean further motion by gravity until it hits the ground, further motion by gravity until it hits the ground. There's no difference at all. So whatever formulae we derived for this particular, body, they are equally applicable for a body which is dropped from a balloon which is moving up with velocity u. But then h should be height of the balloon when the stone is dropped. Fine? Same thing, I mean u by g plus v by g, or, okay, time will be u by g plus root over u square plus 2gh by g. And speed with which this particular stone hits the ground, this one. All they are valid, fine. Projectile motion. A body projected in an inclined direction to the horizontal is called a projectile. The only physical quantity which affects the motion of a projectile is acceleration due to gravity, which is vertically downward, neglecting air friction. Okay, the advantage projectile motion offers us is, we can resolve this motion into two mutually perpendicular directions, horizontal and vertical, or in fact in any two mutually perpendicular directions. Conveniently, I am resolving along horizontal and vertical. Okay, and we can independently study each of this, because we know vectors in vertical direction do not interfere in this direction, and vectors in this direction do not interfere in vertical direction. Component of a vector at 90 degree to that particular vector is 0. So that advantage we will use to resolve this projectile motion in two mutually perpendicular directions, and let's just first study horizontal part of the projectile motion. It's pretty simple. We know very well, acceleration due to gravity is vertically downward. Its horizontal component will be 0. And we know acceleration is rate of change of velocity. When acceleration is 0, change in velocity is 0 means velocity should remain constant. In horizontal direction, acceleration is 0. In horizontal direction, acceleration 0 for a projectile means horizontal component of velocity, that is u cos theta, that remains constant throughout the journey. Okay, so whether the projectile is here, here or here, u cos theta will remain constant. So in horizontal direction, velocity is constant. So displacement at any time t, just ut, no half it square, but for u, you will be writing u cos theta. U cos theta into t or ut cos theta. Okay, this simple equation gives you horizontal displacement at any time t. I'm not telling this is going to be the whole range. Okay, it will give you horizontal displacement at any time t. I mean, if in this equation we write t as 1 second, then x will be u cos theta. That means, suppose projectile is here at t equal to 1 second, then this particular equation doesn't give you displacement, doesn't give you distance, arc length, doesn't give you height. It just gives you how far horizontally body has traveled in 1 second. That is u cos theta, right? This much. Alright. And in the same equation, if you write t equal to 2 seconds, that means particle is somewhere here, suppose, at the topmost point. We don't get height, we don't get distance, we don't get displacement. Okay, we get this value 2u cos theta. How far in x direction horizontally the body has traveled, only that we will get from this equation. Is that clear? At t equal to 3, particle is here. So, okay, x will be this much. At t equal to 4, particle hits the ground, suppose. Then x will be this much. That is range. In this equation, if t becomes time of flight, only then x becomes range. Otherwise, that equation gives you horizontal displacement at any time t. Suppose particle is here, somewhere at 3.5 seconds after projection. What is the value of x? It will be this much. Alright. So, okay, when t becomes time of flight, then x becomes range. Fine. Now coming to the vertical part of projectile motion. It's pretty simple. We have already studied vertical motion under gravity, where a body was projected up with initial velocity u. Its acceleration will be g down. Okay, over here when we are dealing with vertical part of the projectile motion, forget about the horizontal motion. Just focus on vertical part of the motion. And when you focus on vertical part of the motion, this part, you see initial velocity is u sin theta and acceleration is g down. Here, for a vertically projected body, initial velocity u up, acceleration g down. Instead of u, we have u sin theta. That means vertical part of the projectile motion is just like the motion of a vertically projected body, replacing u with u sin theta. And here we have seen time of ascent as u by g. Obviously, in this case, time of ascent is going to be u sin theta by g, right? Just for u, we will be writing u sin theta. Time of flight is 2u sin theta by g, because here it is 2u by g. For u, you need to write u sin theta, that's all. Okay, max height, here it is u square by 2g, max height. Okay, and here it's going to be obviously how much? For u, we will be writing u sin theta, h max. For u, u sin theta, u square sin square theta by 2g, fine. Alright, and here velocity at time t, for a vertically projected body, t second of projection, v is u minus gt. Okay, for u we will be writing u sin theta here. Here we won't get the entire velocity, we get vertical component of velocity of a projectile at time t will be u minus, for u we will be writing u sin theta minus gt. We won't get entire velocity like this, we get vertical component. Only vertical part of the projectile motion we are focusing, right? And we know height of this projectile, vertically projected body, t second after projection is given by height is ut minus half gt square. Taking upward direction positive. For a projectile, instead of u, we will be writing u sin theta, and definitely height, if I call it y, this is I'm calling x, this is y, that will be, instead of u, I'll be writing u sin theta. So this will be ut sin theta minus half gt square. It will give you vertical displacement of a projectile, t second after projection. Fine. We have seen for a projectile, vertical component of velocity at time t, u sin theta minus gt. Okay. Now, suppose u sin theta is 30 and g is 10. As time increases, say, when t becomes 1, 2, 3, exactly when t is 3 seconds, 30 minus 30, 0, vertical component becomes 0. Okay, one moment later, when t becomes 3.0001, vertical component becomes negative, means body has already started coming down. Okay, a moment before that, 2.999, vertical component is still positive and the body is still going up. Fine. Now, at the topmost point, where vertical component of velocity becomes 0, that means at the topmost point, entire velocity is going to be horizontal, because we know that particular component doesn't change. Okay, so at the topmost point, angle between velocity and acceleration for a projectile is 90 degree, and only at that point speed of the projectile is going to be minimum, not zero, but it's going to be u cos theta, entirely horizontal. Fine. Velocity of a projectile at time t will try to compute. We know horizontal velocity will be u cos theta only, it doesn't change. Okay, suppose velocity initially makes an angle theta, and t second later, suppose this particular velocity becomes v and it makes an angle alpha with the horizontal. Okay, so now this vertical component vy is this, and the entire velocity, this one, is going to be under root vx square plus vy square. Fine. Okay, so velocity at time t seconds after projection is going to be root over vx square plus vy square is going to be u square cos square theta plus u sin theta minus gt whole squared. Fine, this thing whole squared. And at what angle it is? It is at an angle alpha with the horizontal given by tan alpha is vy by vx. So we can safely write tan alpha equal to vy is u sin theta minus gt, okay, by u cos theta. Alright, so if alpha is given we can get t, if time is given we can get alpha. Alright, this formula can be used to find like how much time a velocity vector takes to turn through so and so degree angle, right? For example, it's given a body projected at 60 degree, after what time it will be moving at 30 degree. Okay, tan 30 is going to be 1 by root 3, plug in here 60, theta is 60, substitute everything, you will get the value of time. Fine. Okay, of course while doing problems we'll be using a lot of common sense methods or shortcuts, but this is a standard method. Fine. As we have already said, in this equation if t becomes time of flight, then x will be range. So range will be u. Range is this horizontal distance reached by the projectile until it reaches the same level as the point of projection. Fine. So u, for t I'll be writing time of flight, which is 2u sin theta by g. Time of flight depends only on vertical part of the motion of a projectile. For cos theta, let me write cos theta as it is. 2 sin theta cos theta can be written as sin 2 theta. So this is going to become u square by g as it is, and here it is sin 2 theta. This is a formula for range for a body projected at an angle theta with speed u. Alright, this. Okay, and this range is going to be maximum when angle of projection is going to be 45 degree for a given speed c, and that max value is going to be u square by g. Alright, sin 2 theta max value is 1, so I'm not writing that, but sin 90 is 1, so 2 theta is 90, so theta will be 45 degree. So at theta equal to 45 degree, okay, for a given speed, range will be maximum, and max range is going to be this much. Fine. We know horizontal displacement at time t is given by ut cos theta, and vertical height of a projectile at time t is given by ut sin theta minus half gt square. Okay, vertical motion is just like the motion of a vertically projected body, replacing u with u sin theta. Fine. Now, what I'll do is from this equation, I can easily get t as x by u cos theta. So far what we have done is, we studied horizontal motion separately and vertical motion separately. Now I'm trying to merge these two. Alright, so this value of t from horizontal motion I'm putting in this equation. So we end up getting y equal to x tan theta minus g x squared by 2 u square cos square theta. Okay, this equation is of the form y equal to ax minus bx squared. Okay, where a and b are constant means even I am taking this g as constant. So this formula is valid only for small heights compared to, radius of the earth, where acceleration due to gravity can be taken as constant. Fine. Basically, this is a linear term, and this is the highest power is square term, linear term, square term. So when you try to take a graph, xy graph, in fact this is equation of a trajectory or trajectory of this projectile, equation of this path, ys graph. Okay, linear term, square term, this is a parabola, this is a general equation for parabola. This shows path of a projectile is a parabola. Now, if we need range, suppose this is the equation given, range. Range is nothing but the value of x when y becomes 0. The body should start from ground and come back to ground. When y is 0, then whatever value of x you get, that's going to be range. So just substitute y as 0. Then we end up getting something like ax minus bx squared. Okay, on simplification we get x equal to, just take the other side, cancel out one x, and you will end up getting something like a by b. That's going to be the range. Fine. We know when a body is projected with a speed u at an angle theta, its range is going to be u square sin 2 theta by g. Okay. Now when we project the same body, or other body, doesn't matter, because in kinematics we are hardly bothered about the mass of the body. Fine. So when a body is projected with speed u, same speed at an angle 90 minus theta, complementary angle, what's going to be the range? r 90 minus theta. Okay, before proceeding here, we need to know sin 180 minus theta is sin theta only. Okay, for 180 and 360, sin will remain sin, cos will remain cos, tan will remain tan. Fine, ratio remains same. For 90 and 270, sin changes to cos, cos changes to sin, tan changes to cot, cot changes to tan. But then in second quadrant, sin is positive, all silver teacups. Sin is positive here, so 180 minus theta is sin theta only. Fine. So coming to range of a body which is projected with speed due to an angle 90 minus theta, this is going to be sin 2. For theta, I'll be writing 90 minus theta here. Alright. By g. This is sin 180 minus 2 theta is basically sin 2 theta only. So we end up getting like this, u square sin 2 theta by g, which is nothing but same as the range for a body projected at an angle theta. So r 90 minus theta and theta is same when you are projecting the same speed. Fine. Okay. It could also be written like this for 45 plus theta and 45 minus theta. Doesn't matter. Ultimately, when these angles are complementary, you can call this alpha and you can call this beta. If this is alpha, this will be 90 minus alpha only. Is it clear? Sum is 90. Range is going to be same. Okay. Only range is same. But we know height is different. When height is different, time will be different. Okay. So let's try to see what is the ratio of the time of flight in this case. For a body projected at angle theta, t will be 2u sin theta by g. Alright. For a body projected at 90 minus theta, t 90 minus theta, 2u sin 90 minus theta is going to be cos theta by g. Okay. Ratio when you try to take. So this 2u by g cancels out. Sin by cos is going to be tan theta. So t theta by t 90 minus theta is going to be tan theta. Fine. And when ratio of times is tan theta, ratio of max sides is going to be tan square theta. Okay. We can safely get that. Ratio of max sides is required, suppose. Now, okay, h for body projected at an angle theta, u square sin square theta. Now, when ratio of time of flight is tan theta, ratio of max side is going to be tan square theta. We'll just check it that. So height for a body projected at theta, h max is u square sin square theta by 2g. Okay? Just like height for a vertically projected body, replacing u with u sin theta. For 90 minus theta, max side is going to be u square sin square 90 minus theta by 2g. For, okay, sin square, 90 minus theta becomes sin 90 minus theta into sin 90 minus theta is cos square theta in fact. And as it is, rest of the things u square by 2g remains same here. So ratio is going to be, you cancel this out, sin square by cos square is going to be tan square theta. So we can safely write that, okay, height theta by height 90 minus theta is going to be tan square theta. Okay, range same. Okay, height ratio tan square theta, time ratio tan theta, range same for two bodies projected speed u at theta and 90 minus theta. Fine. Let's now try to get into relative velocity. Velocity of body A relative to B is VA minus VB. Okay, mathematically that's velocity of A plus of minus VB. But how do you understand it? It's like velocity of A relative to B means velocity of A as seen by B, assuming B at rest. For example, suppose A is traveling towards north with a velocity of 5 meters per second and B is moving towards north with a velocity of 2 meters per second. What about velocity of A relative to B? Means velocity of A as seen by B, assuming B at rest. Okay. See, if equal velocity is added or subtracted from all the bodies in the universe, relative motion will not change. Like if, my two hands are now moving up with say, 10 meters per second. If it becomes, 5 down for both bodies or 10 plus 2, 12 up, doesn't matter, relative motion doesn't change. Is that clear? If equal velocity is added or subtracted from both the bodies, relative motion will not change. Velocity of relative to B means velocity of A seen by B, assuming B at rest. B at rest means this should become 0. That means we are subtracting 2 to make it 0. Now, we should also subtract 2 from this body so that the relative motion doesn't change. So this 5 minus 2, now it becomes only 3. So, okay, velocity of A relative to B is just 3 meters per second now. Okay, because we are assuming B at rest. If B assumes that I am at rest, how the A appears to move to me? That is velocity of A as seen by B. Velocity of A relative to B. Is it clear? It's pretty clear if you try to understand. Suppose A or B in a race. And okay, A is traveling with a velocity say 50 meters per second and B is traveling with a velocity say 20 meters per second. In 1 second, B will be 20 meters away, whereas A will be 50 meters away. B is here, A is here. So relative to B, A has traveled only 30 meters, so velocity of A relative to B is 30 meters per second, something like that. By definition, it is, velocity of A related to B is VA minus VB, which you are ending at 30 meters per second over here. Is that clear? Similarly, acceleration of body A related to B is mathematically like this. That's basically acceleration of A plus of minus acceleration of B. Negate and add it. But then how do you feel it? How do you understand it? Acceleration of A related to B. Velocity of A related to B is velocity of A as seen by B assuming B at rest, or assuming B's velocity is 0. Similarly, acceleration of A related to B is acceleration of A as seen by B assuming acceleration of B 0. That means we are assuming that B is either at rest or is moving with uniform velocity. Okay? Mathematically it is something like this. We can also understand relative acceleration in a different way. We know acceleration is change in velocity by time. And when acceleration is 0, change in velocity is 0, or velocity remains constant. Velocity is constant means path will be straight line for the body. Fine. Now, relative acceleration can also be written as change in relative velocity by time. Rate of change of relative velocity is relative acceleration. Okay. Now, if relative acceleration is 0, acceleration of one body with respect to other body is 0, change in relative velocity is 0, or relative velocity remains constant, or velocity of one body as seen by other body will be constant means, okay, path of one body as seen by the other body will be a straight line with uniform speed. Clear? Now, suppose a body is projected with velocity u1 at an angle theta 1, and another body is projected with speed u2 at an angle theta 2 to the horizontal. Or you can throw in different directions. U1 at an angle theta 1, U2 at an angle theta 2 in different directions. Need not in the same vertical plane. Now what will be the path of one projectile as seen from another projectile? We know, irrespective of the direction and velocity with which you throw, both the projectiles do have the same acceleration to gravity, g. So relative acceleration is going to be 0. When relative acceleration is 0, relative velocity will be constant. That means velocity of one projectile as seen from another projectile will be constant means they appear to move to each other in a straight line with constant speed. So path of one projectile as seen from another projectile is going to be a straight line. Suppose two students A and B are just coming down in a lift, okay, from a tall building. And suppose over a small coil, B throws A out and is falling in a parabola like this. Suppose A is somewhere here. Okay, B is still in the lift. C is standing on the ground. Path of A relative to C or as seen by C will be parabola with acceleration g down. We know very well. If we are sitting in a train and train is moving in this direction with 10 meters per second, it will appear as if the world is going back with 10 meters per second. Tree standing on the ground will appear to go back with 10. If our velocity increases from 10 to 20 in that direction, it will appear the velocity of stone increases from minus 10 to minus 20. Okay, so if I am accelerating at A in this direction, it will appear as if tree is accelerating with minus A in this direction. Same thing over here. Okay, path of A related to C is, parabola with G down. Path of C related to A, it's like this parabola, it will be like this parabola. Path of C as seen by A will be this parabola with acceleration G up. Alright, now coming to this. Okay, suppose this string snaps and lift is falling freely. Okay, path of this B, freely falling lift as seen by this C is, straight line with G down. Okay, similarly now, path of C related to B will be straight line up, G up, right? With G up. What about now, path of A related to a person which is falling freely inside the lift? Acceleration G, once again relative acceleration 0, once again relative velocity will remain constant means path of projectile as seen from a freely falling lift is also straight line, relative velocity constant, relative acceleration 0, right? We have already seen velocity of one projectile as seen from another projectile is constant in both magnitude and direction. So path of one projectile as seen from another projectile is a straight line. Okay. Now, what is the condition for this path to be a horizontal straight line? We know we do not feel velocity, we feel velocity differences. Earth is carrying us with almost a velocity of about 32 km per second on an average around the sun. We don't feel it because even we do have the same velocity. We don't feel velocity, we feel velocity differences. We don't feel pressure, we feel pressure differences. We don't feel temperature, we feel temperature differences. We are good at feeling differences. If somebody is like, just like us, we don't feel, but if somebody is different, we do feel it, right? We are good at feeling differences. Now coming here, suppose this body is projected with U1 at an angle theta 1, body is projected with U2 at an angle theta 2. Now, Okay, we want the velocity of one projectile as seen from another projectile to be a horizontal straight line. Means we want to feel horizontal, means we don't want to feel vertical, means vertical motion should be similar. Because we don't feel similarities, we feel differences. Vertical motion should be similar means u1 sin theta 1 should be equal to u2 sin theta 2. When vertical velocities are equal, okay, and when they are projected at the same time, then when this particular body is here, then the other body will be here. When this is here, this will be here. Okay. And then when this body is here, the other body will be here. When this body is here, the other body will be here. Okay, they will be at the topmost point at the same time because, you know, time of flight, 2u1 sin theta 1 by g. Here it should be theta 1, sorry. Okay, this should be 2u2 sin theta 2 by g. Time of flight is same because, you know, these are same. Is it clear? Ratio is 1:1. So both will reach at the top at the same time. And when this body starts coming down and somewhere here, suppose, then the other body will be somewhere here. They will be at the same level. Okay, they will appear to each other as if they are moving horizontally, like this. Fine. So, relative to each other, path will be horizontal straight line. Mind you, they need not move in the same vertical plane. I mean, they will be in the same horizontal plane. You can even throw in one different direction, in different vertical planes, but they will be in the same horizontal plane, right? What I mean is, you need not throw them in opposite directions, opposite planes like this. In the same vertical plane in opposite directions, you need not throw. You can throw in different directions, keeping 30-degree angle between the vertical planes also. Even in that case, the horizontal plane is same, that's enough. Is that clear? So this is a condition for path of one projectile, as seen from another projectile, to be a horizontal straight line. Vertical motion should be similar. Is that clear? Now, already you might have understood. What is the condition for the path of one projectile, as seen from another projectile, to be a vertical straight line? In that case, you need to throw it like this, suppose. Now, both will be in the same vertical plane. Okay, obviously horizontal plane will be different. If this particle is here, the other should be here. If it is here, this should be here. If it is here, other body should be here. If it is here, other body should be somewhere here. So, relative to each other, they are moving vertically. Relatively, they are moving vertically. We are seeing here vertical motion with respect to each other means, they are seeing vertical motion with respect to each other means they are not seeing horizontal motion means. Horizontal motion should be similar. Okay, so this much. They are equal, right? So horizontal motion should be similar means, obviously, horizontal velocity should be same. That is, u1 cos theta 1 should be equal to u2 cos theta 2. Now, this is a condition for path of one projectile as seen from another projectile to be a vertical straight line. They will be in same vertical plane and should be projected at the same time. They will be in different horizontal planes. Clear?